Hello people, this video segment is for chapter 3, which deals with modeling of a universal joint mechanism in CATIA. So let me show you first what the plan is. I would like to create this mechanism, and I think it's instructive for me actually to make the parts, although they are simple, but I think it gives a good idea of how I go about doing this problem. Making the part probably takes about 4 or 5 minutes, and then we put it together as a mechanism. Okay, so let me, ignoring all the dimensions, let me start with the product file. So file, new product, and right away I'm going to save this thing. File, save management, save as. On my desktop, I create a new folder, and I will call it universal joint mechanism. Okay, the first thing I'm going to do is create an orientation part. Its sole purpose is to make sure that when we create these shafts of the universal joint, we can easily position them. So insert a new part in there, and I will call this thing orientation. Right click, properties, orientation. It has no other function. Orientation. Okay, let's make it. So double click on this. On a convenient plane, on that vertical plane, I will draw a broken line segment like so, where the angle between them is between these two lines is 60 degrees. This is the angle of the two shafts, as you will see later. So let's make it 30 degrees. All right. Good. Exit, and obviously save. Save it. Let us now go and make the shaft. So insert new part in there. I'll say no, and right click, properties, shaft, and shaft. The two shafts are identical, so I will make only one of them and use an instance of that for the other piece. So let's make it. On a convenient plane, for me this vertical plane is convenient. I'm going to draw the basically the grip of that of the two shafts. We'll clean it up in a second. Something like this. I'm going to make it nice and symmetric with respect to the horizontal axis. So this line, control that line, control the middle axis, symmetric, and this line, the bottom line, and the middle line, and symmetric. Okay, since there are no dimensions specified, these can be resized until we're happy, and this looks good. Exit, pad it in both directions, and let me make this thing point maybe 0.4. Okay, yeah, that looks fine. Okay, now on that top plane, I will draw a circle because you want to make a hole so that the crossbeam is going to be positioned in it. So, you know, something like that. Exit. Make a pocket all the way through into the last. All right. Now let's make the actual shaft at this end. So let's draw a circle. There we are. Exit and pad it to the length that we are satisfies me. So this is going to be, yeah, that's fine. Let's make it 5. All right, good. Now, for a reason that becomes clear in a few minutes, I would like to create a point exactly halfway between the center of this circle and the circle underneath. So let's create a point here. Where are the reference elements? There is a point. And the way we want to do that, we want to say between. Well, it's going to ask us between what point. So, okay, I want to create a point at the center of this top circle. So right-click, create a point. And the method of creating the point is center of circle or ellipse. So there is my circle. So notice that it temporarily created a point there. And then it's asking you for the second point. I do exactly the same thing, create a point. And for the circle, I'll take this bottom one. Again, temporarily creates a point there. And it says, okay, you created your 2 points. Where do you want the middle point to be? Obviously, it's exactly halfway. So either I can say middle point or put 0.5 here. It'll do the job. So notice that it did create a point for me. It's right there, as you can see. And I will be using that later on for the purpose that I have in mind. Okay, so let's save everything. I can insert the second shaft because I saved it. I can say insert existing component in there, and I go to that folder that I created. I think it was called Universal Joint. Let's see if we can find it here. Let's see now, this one. This is the one that I created, and I called it shaft. I bring it out. And the two are going to be superimposed on top of each other. The two are sitting on top of each other, so we can actually, let's see now, we can move these things so that they don't interfere with the rest of our work. Might as well rotate about the z-axis. Oops, there we are, and also translate it in this direction because later on I'm going to mount it on that other end. Right now it's not that critical, but we're going to do that later. All right, so let's actually go ahead and do the pin. So save everything, insert, new part, say no. This is the cross pin, so I'm going to call it right-click properties, cross pin, and cross pin. All right, and let's make it. So on a convenient plane, on that top plane, I will sketch. I want to sketch a circle that size, so why don't I just project that circle, one of these circles. There we are. See it right there. Exit, and then we pad it. And we pad it until the bottom plane, until the plane up to this plane, and the plane is right there. Okay, so that's the half of the cross pin. Now, to create the other one that is perpendicular to that, I will use this trick of making a circular pattern. 2 instances, total angle is 90 degrees. And the thing that I want to pattern is that path. And the reference element means what is the axis of symmetry type thing. So either you take the axis of the shaft or this line, and notice that it did create it over there. Okay, that's an easy way of making this whole thing. All right, so let's actually go ahead and save everything. So let's go to the top level assembly. That's my favorite way of doing. Save everything. All right, there are no assembly constraints here. So let's actually move stuff out of the way. Let me move the cross pin out of the way. I'm going to translate that in the Y direction. There we are. And there is no constraint, there is no assembly constraint between the shaft and this line. So I make a coincidence between the axis of the shaft and this line that I created, orientation. Remember orientation that I created? actually not that one. Oh, sorry, the other side. So undo this, try it again. Coincidence between the axis of the shaft and, let me see, okay, there. This is the piece of the orientation on this side. Nothing is updated, nothing is there to update because that was already, they were already coincident. Okay, now I also want to push this point to that center point. See that? This point that I created here, I want to put it exactly at the break line. So coincidence between that point and this origin. And update, so it's going to push the shaft to the left. Now let's insert a crosspin. So coincident between the axis of the pin and this, and also coincidence between the axis of the pin here and that guy. Coincidence between the axis of the pin. Well, actually, let's not worry about that because I have to do that after a. Let me update this. There we are. Okay. Don't worry about the other one right now. So let's place this other shaft on that orientation line. So coincidence between the axis of the shaft and this, and update. Good. And then coincidence between this point and that point that is right at the break point, and update. So all I have to do is to make sure that these are lined up. Coincidence between the axis of this hole and the axis of this crosspin. And by the way, I forgot to do something. It makes it a lot easier if I anchor something. So I'm going to anchor the orientation right there. Okay, and now update. All right, good. Excellent. So this is pretty much it as far as making the parts is concerned. So let's save everything. And now we go and do go to the digital mockup. So digital mockup DMU kinematics. Get the magic wand out. There's a magic wand. So the joints that we created, we're going to convert them into the constraints that we created. We're going to convert them into joints. So new mechanism, auto create. Okay. Now let's check what we've got. See what we've got. We got several cylindrical and one spherical. The reason that we have a spherical is that we put the 2 points coincident to each other. So first of all, I don't need this. Delete. All right. And what I would like to show you is something interesting, and that is well, first of all, degree of freedom, it says it's 1. Okay, so let's see now. Let's take one of these. Let's take one of these and make it angle driven. For example, we take let's see now. This is shaft 1. The crosspin is shaft 1. Shaft 1 cross shaft 1. This is shaft and orientation. That is this guy, as you can see. Make it angle driven between 0 and 360. Because mechanism can be simulated, and let's try it now. You can do that manually right there. You see, we have the universal joint working, and you know, this is fine. We did it, but I never actually used this universal joint that you see here, right there. Okay. This thing works. There's no problem, and I can put physics in it. But the question becomes, what is the purpose of this universal joint here? Okay. Now notice that the role, this cross pin, really its role is secondary here, because if you want to make sure that motion is transferred from this shaft to that shaft, according to the laws of physics, according to the laws of universal joint, then we really don't care about that pin. As a matter of fact, I can go and entirely delete the cylindrical joint between the pin and these shafts. So let me delete this, and let me delete the other one right there. Delete the other one. All right. Obviously, the degree of freedom is 2 here, and it won't simulate. So now I can use this universal joint icon here, and for spin 1 I select the axis of this shaft. For spin 2 I select the axis of the other shaft, and you can leave these things the way they are. It's really not critical. As a matter of fact, the documentation about the meaning of normal to spin 1, normal to spin 2 in the online documentation is pretty bad. And in fact, if you try to find references to this terminology in textbooks or research books, you don't see anything. So I'll just leave it the way it is, and it works without it. And look what happened. So mechanism can be simulated. Okay, so let's see now. For example, right there. Except that the pin will not move. If the motion of the pin, cross pin, is not important to you, don't worry about it. Just create 2 cylindrical joints. In this case, one is revolute, the other one is cylindrical. Depending on how you do it, it could be that these are both cylindrical and universal joint will do the job. Okay, so hi people, this is a tutorial from chapter 9 of the textbook Mechanism Design and Animation. It deals with the simulation of a planetary gear, or more specifically what is called epicyclic gear. And in that particular problem, I did this thing in class for the case where the ring gear was fixed. So what I would like to do today in this video segment is deal with the case where the sun gear is fixed. And notice that if that is the case, you're in the overdrive mode and the gear ratio is 0.71. We'll talk about this thing later on, and in fact verify these things through the CATIA simulation. I'm assuming that the sun has 30 teeth, and the ring has 72 teeth. And since the number of teeth are proportional to the radius of the particular gear, I'm going to assume that the sun has a radius 3 inches, and the ring has a radius of 7.2 inches. Okay. Here's the situation. It is made. This thing is made of a ring, which is the yellow one, a sun that is the green one. The planet is this orangish, and the carrier is right here, this long rod, and there's a shaft in the back that is sitting stationary. These are very simple parts to make. However, I think it's still worth giving it a shot, and it's going to take me about maybe 5-10 minutes to make these parts. And once we make it, then it's easy to put it together. So I'm going to close this thing, insert, so file, part, new, product. All right, let's insert a new part in there. And let's start with the sun. Okay, so I'm going to rename this thing to be the sun. Sun and sun. Okay, let's make this on this vertical plane. I'm going to sketch a circle of radius 3 inches. Let's change this into radius 3 inches. Okay, and exit. Oh, I'm going to make a little hole here, little circle here, which eventually turns into a hole, because we want to plot the angular velocity, and we need to create sensors. Therefore, I need some identifiers here. So anyway, so there we are. Exit and pad it by. Okay, we got to go to wireframe to part design, and then pad it by. Let's make them all 0.5 inches. 0.5 inches. Okay, there's the sun. All right. Let me also change the color to yellow. Actually, I think in the original the thing that I showed you, I made it green. So let me make it green. Okay, good. Now insert. Let's make the ring next. Insert new part. Let's do it like that. Insert a new part, and let's call this thing the ring. So right click, properties, ring and ring. Ring and ring. So this is going to be something that has a radius 7.2 inches. So let's make it on this same plane, vertical plane. I will sketch, zoom out, a circle which is radius 7.2 inches. 7.2 inches. And since we wanted to have a three-dimensional, three-dimensional aspect to it, I'm going to make a little ring outside and put a marker here because we're going to plot angular velocities later on. There we are. Let me see now. I didn't really want this thing to be tangent, so let me. No, it's not tangent. Okay. All right. So exit and pad it 0.5 inches. Okay, there we are. Alright, it's very close to that border. That's irrelevant. Actually, you know what? Let me go ahead and clean this up. So let me go to this pad, this sketch. I want to delete that tangency and then make this thing smaller so that we don't have some issues later on. Alright, good. Let's make this thing, I think I made it yellow. Alright, now let's make the planet. So go there, insert, new part, and we make this thing the planet. Right click, properties, planet, and planet. Planet. Let's make it. Double click on a convenient plane, on that vertical plane. I will sketch. There we are. A circle, and then we're going to make a tangent to both. Okay. There we are. So we make this, control that. Where's that? Tangent to each other. And this and that guy also tangent to each other. Sorry. Let's see now. This, control this, tangent to each other. Alright, and let's make a little circle here so that you can see the rotation of these things later on. Alright, so pad it 0.5, and if I'm not mistaken, I made this thing orange. Colors don't matter, but I want to be consistent with what I showed you before. Alright, let's do the shaft. The shaft is sitting in the back. Okay, so insert, new part in there. Let me call it the shaft. Properties, shaft, and shaft. and let's make it. On that back plane, I will sketch a little circle. Here we are. Exit. Okay, and then pad it. Let me see this back plate. Okay, there we are. Okay, that's. Oh, sorry. Let's flip. Let me flip this thing. There we are. This is a shaft. Okay. Okay. Now finally the carrier. So double click, insert, new part in there, and let me call it the carrier. Properties. Carrier and carrier. I think carrier has 2 R's. Okay, that's good. So let's make it. Now on that front face, I will sketch. Okay, something that looks like that shape that I had in my original drawing. I'll clean it up in a minute. Okay, so let's go here. Okay, let's first of all make sure that this line and that line is symmetric with respect to this. I think it is, but anyway, just shift it a little bit. Let's make sure that this control that, these are concentric. Alright, and the same thing down here. This guy control that guy, make it concentric. Some of these are not necessary, however, I would like to follow. Alright, so there's the carrier, and I will actually make a little indentation here, a circle here, which eventually will turn into a hole once I pad it. So pad it, 0.5. There we are. And this thing, I believe I made it, if I'm not mistaken, that color. Now something I forgot to do, and I'm going to do that right now, is I would like to create a point at the center of each of these circles, because we're going to be creating sensors and then plotting the angular velocity, for example, at some point. At that point, we're going to make it easy to make it the center of these. So let's go to the, for example, this is the planet. Double click on it. You're there. Make a point. And the method of making the point is going to be circle center. Right there, and there is the point. So a point has been made right there. You can see that. And then I'm going to do one in the carrier. Double click on the carrier so that I go into the carrier part. And I don't know why did this thing double. First of all, let's make the size of this 0.5. That's good. Okay, fine. I don't know why it became okay. Let me make this thing 0.25 actually. But that was not the issue. I want to make a hole right there. So a point at the center of that circle. That circle is made. You can see that there's an X there. And now we're going to go to the ring. Double click on the ring. There we are. And make a point at the center of that circle. Whoa. Let's try it again. The center of that circle. I think I have to zoom in. There. There. The point is made. And finally, I'm going to go to the ring. Double click on the ring. Let me hide this. And make a, are we in the ring? I think we are. Make a point at the center of, let's see, cancel. Okay, zoom in. A point, center of this. All right. Okay. So all the parts are made. However, I'm not going to create assembly constraints. I will go and create all the joints directly in the digital markup. Maybe a good idea to save this thing. I'm not sure. Just leave it the way it is. So we go to the digital markup, DMU kinematics. And okay, so first I'm going to anchor the shaft. So new mechanism, mechanism 1, anchor the shaft. Okay. Then because these two, because the sun is fixed, I create a rigid joint between the shaft and the sun. Shaft is stationary, so the sun is stationary. Let's create some revolute joints. Revolute between the axis, between the carrier and the sun. Okay, or not the sun, the carrier and the gear. So axis and axis, and then plane of the shaft and plane of the gear, but there's an offset because the planes that I'm taking, they have offsets in it. Okay, let's do another one, another revolute between the carrier and the sun, for example. Oh, it really doesn't matter where the shaft because it's going to both stationary. So another revolute between the axis of the carrier and the axis of the sun, plane of the carrier, plane of the sun, and there is an offset involved. Okay, one between the carrier and the planet, revolute between the axis of the carrier, axis of the planet, plane of the carrier, plane of the planet, and there is an offset there. Okay, now my strategy is instead of making gear joints, I'm going to make roll curve joints. So roll curve between this arc, this circle, and the circle of the ring, and another roll curve between the perimeter of the planet and the perimeter of the sun, and we say okay. Now if you check your let's check these things, check our joints. There should be 3 revolutes, 2 roll curve, and 1 rigid, and degree of freedom should be 1 unless I made a mistake somewhere. Yeah, degree of freedom is 1. You can see that there is 1 rigid, 3 revolutes, 2 roll curve. Now, since our gear is, our ring is the input, so I'm going to make the revolute joint between the ring and the shaft as angle driven. So let's see now, where is this shaft and the ring? Right here. We're going to make this thing angle driven, 0 to 360. We say obviously the mechanism can be simulated, and you can do that manually, and you see that everything works. This is fine. Now we have to put some physics into this. The first thing I'm going to do is to create some sensors here before I put the physics into it. And the sensor is here, the ball rolling down a ramp right there. It's been an acceleration sensor. The first one I'm going to make is going to be the sun. Obviously the sun is stationary, so the angular velocity of it is going to be 0. We know that. And the reference product is going to be the shaft that's stationary, and the point is going to be that point which sits on the, right there, I can selecting it on the sun. Okay, good. Let's make another one, another sensor. Let's call this thing carrier, and the reference product is in the shaft, and the point is the point on the carrier, which is right there. Do another one. This one is the ring, by the way, which is our input. The input is going to, or the reference product is going to be the shaft, and the point is going to be the point on the ring, which is right there. And finally, it is the, which one is it? the planet. Okay, so another sensor. This is going to be the planet, and reference product is the shaft, and the point is going to be the point on the planet, which is right up there. Okay, let's put some physics into the problem. Click on f of x, click on the mechanism so that you get the command associated with the mechanism right here. The formula, let's assume that the ring turns at 60 RPM, which is 360 degrees per second. So 360 G times, or let's say divided by 1s, 360 degrees per second, times the time. All right, and let's do the simulation with law right there. Simulation with law. Activate the sensor, and everything that we want is angular velocity. So let's see now. Sun's angular velocity, which is our angular speed, right there. You select this thing, that turns into a yes. Scroll down, carrier angular speed. Select that, that turns into a yes. Scroll down, ring angular speed. And finally, the planet angular speed. Okay, move this thing down, get it out of the way. Let's do a simulation for maybe a 3-4 second interval. Make it 4 seconds. And I don't have to go that, well, I'll change this into 80. I mean, the bigger this number is, the longer it's going to take. So, okay, so let's play it. After the 4 second expires, this thing stops, and we're going to say graph. All right. So what we're getting here is, let me zoom out of this so that we have more room to display these things. Okay, a little bit more. Okay, so we have 4 curves. Let's look at the one which says sun angular speed. Sun is stationary. You click on it. Notice that the yellow curve corresponds to the sun angular speed, RPM, as you can see, and of course it's 0. Let's do the ring angular speed. Needless to say, that's the red one, and the scale is red, 60 RPM. That was our input. So if you look at the carrier, carrier is the green one, and it shows you that it is around 42. In fact, if you put the cursor on it, right underneath in this white area, you see the actual value, which is 42.7, something like that. Okay. And if you select the planet and you put the cursor on the blue one, it says it's around 102 RPM. How do these match with our calculations? Okay, so here's the situation. The ring RPM was 60. Number of gear teeth on the sun is 30. On the ring is 72. So the gear ratio, according to the table that I showed you at the beginning, is 0.706. So if you take the 60 RPM, the input, multiply it by gear ratio, you get 42.3, which is very close to what CATIA gave us. Now, what is that 102? Where is that 102 coming from? Keep in mind that the planet not only rotates through the rotation of the sun, but it also spins about its own axis. So this thing is actually this 42 is the spinning angular velocity, but it also goes around the axis of the shaft at basically you add the 60 to it because it goes around at the 60 RPM because attached, it's going with the ring. So 60 plus 42 is about 102. So it agrees with what CATIA gives us, and that completes the tutorial.